Find a complete solution of the given equation, which is y double prime plus 4y prime plus 5y equals 2e to the x. Take note that this equation is non-homogeneous since we have 2e to the x here, and constant coefficients since there's no other coefficients aside from the x. So, solution. Take note that to find the complete solution of the given equation, we need to find yc, which is the complementary solution, and yp, which is the particular solution. So let's begin solving for yc. So we let y equals e to the mx, differentiate y prime equals m e to the mx, while double prime equals m squared e to the mx. So substitute this to the original equation. So upon substituting, we get this. So m squared e to the mx plus 4 m e to the mx plus 5 e to the mx equals 0. So we'll let this equal to 0 to solve for yc, and since yc is the solution for the homogeneous part of the given equation, so upon simplifying, we get m squared plus 4m plus 5 equals 0, and this is what we call the auxiliary or the characteristic equation. So we need to solve for, or we need to find the values of m here. So using this equation, the quadratic equation, which is negative b plus minus square root of b squared minus 4ac all over 2a, wherein our b is 4, so we have here 4 plus minus b squared, we have 16, so 4 is ac, which is rc is 5, so 20, so 16 minus 20, we have negative 4. So square root of negative 4, we get 2i, so negative 4 divided by 2, we have negative 2 plus minus 1i. So we have a conjugate pair complex roots, so our yc will look like this. Yc is equal to e to 2x, which is open parenthesis c1 cosine of x plus c2 sine of x close parenthesis. So wherein c1 and c2 are arbitrary constants. So negative 2 is our alpha and 1 here is our beta. So we have now the value, the equation for our yc. We need to find the solution for yp. So we can solve yp using two methods. We could use variation of parameters or the undetermined coefficient. In this example, I use the method of undetermined coefficient because it is simpler than the variation of parameters. So this is the original equation. So I let yp is equal to a e to the x. So I need to find the value of a so that I have now the equation for yp. So y equals a e to the x, differentiate y prime equals a e to the x, then y double prime equals a e to the x. So I need to substitute this to the original equation. So upon substituting, this will now look like this: aex plus 4a e to the x plus 5a e to the x equals 2 e to the x. So I need to find the values of a. So 1 plus 4, so we have 5 plus 5, so we have 10. So we have 10ex, so 2ex divided by 10ex, so we have 1/5. So our value of a is 1/5. Then substitute this, so we have now our yp, which is 1/5 e to the x. We now have the solution for our yc, and we have now the solution for yp. So we could have our general solution, and our general solution would look like this. Y to the x equals yc plus yp. Substitute, so e to negative 2x, open parenthesis, c1 cosine of x plus c2 sine of x plus 1/5 e to the x. This is now the general solution of the given equation. And for our second example, find a complete solution of the given equation. So y double prime plus 4y prime plus 3y equals x minus 1. So as you notice, this looks like the same with our first example, with constant coefficient and non-homogeneous. So we solve this using the same steps, the same approach with our first example, and the same method will be used. So solution. Take note that the complete solution will be equal to yc plus yp. So we need to solve first the complementary solution, or the yc. So we let y equals e to the mx, then integrate, differentiate y prime equals m e to the mx, y double prime equals m squared e to the mx. Then substitute it to the original equation, or to the given equation. So this will look like this: m squared e to the mx plus 4m e to the mx plus 3 e to the mx equals 0. Take note that the yc, or the complementary solution, is the homogeneous solution, or the solution of the homogeneous part of the equation. So we equate the equal to 0. So upon simplifying, we get this equation: m squared plus 4m plus 3 equals 0, which is what we call the auxiliary, or the characteristic equation. So now we have to solve for the values of m using, you can use the quadratic formula, which is equal to negative b plus minus square root of b squared minus 4ac all over 2a. So take note that our a is equal to 1, our b is equal to 4, and our c is equal to 3. So substitute. So our b is negative 4 plus minus square root of 16 minus 12 all over to 2. So we have m equals to negative 2 plus minus 1. So we can have two values of m. If we use the plus sign, we can have m equals negative 1. But if we use the negative sign, m is equal to negative 3. So we have real distinct roots. Our m1 is not equal to m2. So our yc will now be c1 e to the negative x plus c2 e to negative 3x. So our m1 is negative 1 and our m2 is negative 3. We now have the yc, so let us now solve for the yp, again using the method of undetermined coefficient. So this is the original equation. So we let yp is equal to ax minus b. Remember that our yp, or this equation, depends upon the right hand side of the given equation. So here the right hand side is x minus 1, so our yp must be equal to ax minus b, and we are going to find the values of a and b. So now we let y equals ax minus b, then differentiate, so y prime equals a, and y double prime equals 0. Then substitute it to the given equation, so we have 0, which is our y prime, plus 4a plus 3 plus open parenthesis ax minus b equals x minus 1. So solving for a, we have 3ax is equal to x, so our a is equal to 1/3. Now let's solve for the value of b. So we have 4a minus 3b is equal to -1. Since our a is equal to 1/3, so substitute it here, and our b will be equal to 7/9. So we now have the values of a and b. So our yp will be equal to 1/3 of x, 1/3 x minus 7/9. We have now the yc and the yp, so we can now have the general solution of the given equation. So y of x is equal to yc plus yp. So the general solution is equal to c1 e to -x plus c2 e to -3x plus 1/3 x minus 7/9. So this two last term is our yp, and the first two terms is the yc. And c1 and c2 are the arbitrary constant. And for our third example, again find a complete solution of the given equation. Y double prime plus y prime equals x plus 2. So we need to find the complementary solution and the particular solution to find the complete solution. So solving for yc, we have m squared plus m equals 0. So this is the auxiliary or the characteristic equation. So we do this similar to the first two examples, that is, we let y equals to amx and differentiate then substitute. So to find the values of m, we could do this. We factor it out, so our m1 will be equal to 0 and m plus 1 equals to 0, so m equals -1. So we now have two values of m that is not, they're not equal, so real distinct roots. So our yc will now be equal to c1 plus c2 e to -x. Take note that e to the 0 is equal to 1, so we only have c1, and our m2, which is -1, so e to -x. Now we need to solve for yp. Again, we use the method of undetermined coefficient. So our original equation, y double prime plus y prime equals x plus 2. Now for our yp, I let yp to be equals to ax squared plus b of x. So the choice of your yp will depend on the right hand side of the equation. So y equals ax squared plus bx, then differentiate, we have y prime equals 2 ax plus b, and differentiate again, we have y double prime equals 2a. So we need to substitute the values into the original equation. So upon substitution, we have this 2a plus 2ax plus b equals x plus 2. So we need to find the values of a and b in order to complete the yp. So we have 2ax equals x here, 2a equals to x. So our a will be equal to 1/2. So solving for b, we have 2a plus b equals to 2. Then substitute the value of a, which is 1/2. So 2 times 1/2 will be 1, plus b equals 2. So transpose. So we have b equals to 1. So our a is equal to 1/2 and our b is equal to 1. Then substitute it to find yp. So our yp will now be equal to 1/2 x squared plus x. We now have the equation, we now have the solution for yc and yp, so we can derive the solution for our general solution. So our general solution will look like this: y of x is equal to yc plus yp. So our yc is c1 plus c2 e to the negative x plus 1/2 x squared plus x. Take note again that c1 and c2 are the arbitrary constants, and the first two terms is our yc and the last two terms are our yp. And for our fourth example, find a complete solution of the given equation: y prime minus y equals e to the x plus 2 e to the 2x. So this is an equation with constant coefficient and non-homogeneous. So we can solve this the same method as we did to our last three examples. So we need to find the yc and the yp. So let us start with the yc. So we need to find the arbitrary or the characteristic equation. So our characteristic equation is equal to m squared minus 1 is equal to 0. So we need to equate it to 0 to find the yc, or the solution of the homogeneous part. So you can say that m is equal to plus minus 1. So real distinct roots, since our m1 and m2 is not equal, so our yc will be equal to c1 e to the x plus c2 e to negative x. Since our m1 is positive 1 and our m2 is negative 1, note that c1 and c2 are arbitrary constants. So we need now to solve for yp. So again, in this example, I solve yp using the method of undetermined coefficient. So our original equation, then my yp is equal to ax e to the x plus b e to the 2x. I put here x since in our complementary equation there is a term e to the x, and since the solution must be independent to each other, so no terms must be repeating. So I let y equals ax to the x plus b e to the 2x. So differentiate, we have y prime is equal to ax ex, so plus e8 e to the x plus 2b e to the 2x. Again, differentiate, so we have y double prime ax e to the x plus 2a e to the x plus 4b e to the 2x. Now substitute this to our original equation. So we have ax e to the x plus 2a e to the x plus 4b e to the x minus close open parenthesis ax e to the x plus b e to the 2x equals to ax plus 2 e to the 2x. So we need to find the values of a and b so that we can have our particular solution. So we have to solve for a, we have 2a e to the x. This term equals to e to the x. So we can solve our a, which is equal to 1/2. Now solving for b, we have 4b e to the 2x minus b e to the 2x equals to 2 e to the 2x. So 4 minus 1 is 3, so cancel all the 2x, so 3b minus 2, and we have the value of b, which is 2/3. And now our yp, just substitute the values of a and b. So yp will now be equal to 1/2 x e to the x plus 2/3 e to the 2x. Since we now have the values of our yc and yp, we can now have the general solution of the given equation, which is y of x equals to yc plus yp. So the general solution is c1 e to the x plus c2 e to negative x plus 1/2 x ex plus 2/3 e to the 2x. Note that the c1 and c2 are the arbitrary constant. The first two terms is the yc, and the last two terms are the yp. And down to our last example, find a complete solution of the given equation, which is y double prime plus y equals cosine of x plus 3 sine of 2x. So again, this is an equation having constant coefficient and is non-homogeneous. So to find the complete equation solution, we need to find the yc and the yp. So first, let us solve for yc. To solve for yc, we need to convert the given equation into its characteristic or auxiliary equation, which is m squared plus 1 equals 0. So transpose 1, so we have here -1, then square root of -1, we have 1 imaginary, or plus minus 1i. So our yc now is equal to c1 cosine of x plus c2 sine of x. Note here that our alpha is equal to 0, so e to the 0 is 1. So our beta is 1, so we have 1 here and 1 here. So we have now the yc. Let us now solve for the yp. And I solve yp using the method of undetermined coefficient. You can solve this using variation of parameters, but I choose the method of undetermined coefficient for simplicity. So I divided the right hand terms into 2, the cosine x, and the other is the 3 sine x. So my yp will be equal to y1 plus y2, which is my y1 is equal to ax cosine of x plus bx sine of x. The x here are added, so since our complementary equation contains the cosine x and the sine x, so they should not be the same, or they should be unique. So differentiating, y1 prime is equal to negative ax sine x plus a cosine of x plus b sine x plus bx cosine of x. So y1 double prime is equal to negative ax cosine of x minus 2a sine of x minus bx sine x plus 2b cosine x. So substitute this to our original equation. We have negative ax cosine x minus 2a sine x minus bx sine x plus 2b cosine x plus ax cosine x plus bx sine x equals to cosine x. Again, I divided the right hand term into two. So this is the first, the cosine x, and the other is the 2 sine 2x. So solving for b, we can cancel this out since we have only cosine x here. So we can cancel this out, cancel this out, cancel this out. So not this one. So we can cancel this out, we can cancel this out. So what remains is the 2b cosine x. So equals to cosine of x. Then our b would now be equal to 1/2. And substituting it, so y1 equals 1/2 x sine x. Now let us solve for y2. I'll let y2 to be equal to c sine 2x plus d cosine 2x. So we need to find the values of c and d. So differentiate y2 prime equals to 2c cosine 2x minus 2d sine 2x. So y2 double prime is equal to negative 4c sine 2x minus 4d cosine 2x. So substitute it to the original equation. So we have negative 4c sine 2x minus 4d cosine 2x plus c sine 2x plus d cosine 2x equals to 3 sine 2x. This is the second term of the right hand side. So we can cancel all the cosine. So what is left is negative 4c sine 2x plus c sine 2x. So negative 4 plus 1 is negative 3. So negative 3 sine 2 c sine 2x equals to 3 sine 2x. So our c is equal to 1. And our y2 now be equal to negative sine 2x. Since we have now our y2 and our y1, equals to 1/2 x sine x, and we'll let our yp to be equal to y1 plus y2. So adding the two terms, we have now our yc, which is equal to 1/2 x sine x minus sine 2x. Since we already have our yc and yp, we can now have our general solution of the given equation. So y of x equal yc plus yp, and y of x is equal to c1 cosine x plus c2 sine x plus 1/2 x sine x minus sine 2x. This is now the general solution of the given equation.